It doesn't matter that I've done it before. I'm going to do it again. The 1D infinite square well, let's find an expression for the wave function. I'm not going to get into all the Schrödinger equation background stuff, even though those are a lot of cool things. But let's just say that I have a particle. It can only exist in between these infinite potentials in one dimension. And it has to satisfy this equation, the Schrödinger equation. So we're trying to find this function psi, capital Psi. And it has to obey this. It says I, the imaginary number I, h bar is a constant, the first partial of psi with respect to time, and that has to be equal to negative h bar squared over 2m, the mass of the particle. The second partial of psi with respect to x plus the potential times psi. It's just a differential equation. So let's just solve this differential equation. Okay, the first thing is that if we are confined the particle in here, and these are infinite wells, then it can only exist here. And in here, the potential, v, is 0. So this makes our equation a little bit easier. We can write it like this. I, h bar, partial of psi with respect to t. And if you think, oh, this is going to be a quick video. No, it's not going to be quick. It's going to be thorough. And I'm probably going to make mistakes, but that's okay. H bar squared over 2m, second partial of psi with respect to x, because that's 0. V is 0. Okay, now the first thing we want to do is to say, okay, is it possible that I could take this function of x in time and make it a product of a function in x and a function in time? So let's assume that psi of x and t is equal to some spatial function psi of x, lowercase psi, and some time function f of t. If I put that in here, then when I take the partial of this with respect to time, it doesn't do anything to the space part. When I take the partial with respect to x, it doesn't do anything to the time. So I can write this as I h bar. I'm going to take the derivative with respect to time, but the psi comes out. I'll leave off the as a function of x. The partial of f with respect to t equals negative h bar squared over 2m. And I'm going to take the partial with respect to space. Nothing happens to the time, so that comes out. Second partial of psi with respect to x. Now that didn't really get us much, except we can now use a trick. Let's use a trick. I'm going to take both sides of the equation and multiply by 1 over f psi. If I do that, over here, I'm going to take 1 over f psi multiplied by this. The psi's are going to cancel. So I get I h bar 1 over f partial of f with respect to t. And over here, I get negative h bar squared over 2m. I have the f's cancel, so I get 1 over psi. Second partial of psi with respect to position. Now, that may not look like much better, but it is indeed much better, because all of my time is on this side. All of my x is on this side. So here I have a differential equation, and this side only changes with time. This side only changes with x. And the only way that can happen, because if I change the x, this side shouldn't change. If I change the time, this side doesn't change. So that means that both sides of these have to be equal to a constant. And we're going to call that constant e. So both of these are equal to e, a constant. So let's take just this. So I'm going to set that equal to the constant e. That's also equal to e, but I have I h bar 1 over f partial of f with respect to t equals e. And now this equation I can actually solve. It's not too terribly difficult. It's a differential equation. Let's multiply both sides by f and divide by I h bar. Partial of f with respect to t is going to be equal to f e over I h bar. All right, all to do is divide both sides by this. Now, we don't like to have I on the bottom, so you can actually do this. I can multiply by negative I over negative I. And then down on the bottom, I have I times I is negative 1. I have another negative right there. So this just becomes negative I over h bar E F. That's right, right? Yeah. Okay. So this says I have some function f. I take the partial with respect to time, and I get this constant times that. Well, what function, when you take the derivative of it, do you get this constant and the function back? And one solution to that is when we can just guess this. And this is what we do in physics. We deal with differential equations that we can mostly just guess with. I can guess that f as a function of time is e to the minus I e over h bar t. And let's just check. If I take the derivative of that, partial of f with respect to time, then I pull that stuff down in front, minus I e over h bar, and then I get the function back, e to the minus e I e t over h bar, and that is f. So this is the same as that. So this does work. Now, I could multiply this by a constant and it would still work, okay? And I think that's important to point out. There could be a constant in there, but we don't need to put a constant there. We do need a constant, but we have that other function, psi, and so that's going to need a constant also. So we can just have one constant, and we'll associate that constant with psi. Now let's go back to our other part of a function right here. Yeah, I'll put this to the side because this is important. We'll come back to that. But now I have this part. So I have negative h bar squared over 2m 1 over psi, second partial of psi with respect to x is also equal to e. And we want to solve this equation. Again, let's do the same thing. Let's get this stuff to the other side. So I'm going to multiply by negative 2m over h bar squared, and psi, I get second partial of psi with respect to x squared is going to be equal to negative 2m over h bar squared psi, and there's an e. E. That's it. Okay. It turns out that it makes our life a little bit easier if we call this k squared. So I'm going to say k squared is, because we get this constant in there. K squared is going to be 2me over h bar squared, or k equals the square root of 2me over h bar. That's just you don't have to do that. It's going to get messy if you don't. So that means that I have the second partial of psi with respect to x is negative k squared psi. Now this is kind of the same situation, but now when we take the derivative twice, we get the same function back with a negative sign. And if you've taken physics before, and I suspect that you have, because you wouldn't be watching this video if you hadn't done previous physics, this looks like a simple harmonic oscillator, the same kind of thing, except space instead of time. But we can guess a solution again, and this is just one solution. I'm going to guess psi of x is a sine of kx plus b cosine of kx. And let's just show that this does indeed work. If I take the partial of psi with respect to x once, I get the derivative of sine is cosine, but then I have to take the derivative of the inside. I get a k cosine kx, and this is going to be the derivative of cosine is negative sine. I get negative b k sine kx. Now I take the derivative again, the second partial of that with respect to x. Here I have negative a k squared sine kx, right? Because the derivative of cosine is negative sine, and the derivative of sine is cosine, so I get negative b k squared cosine kx. And this is negative k squared times psi, because psi was a sine kx plus b cosine kx. So it did work. Yay. But we don't know a and we don't know b. So we got to find a and b using our boundary conditions. So our boundary conditions, we know that if the wave function represents part of the probability of finding the thing, and we know that you can't find it over here, and we know that it has to be continuous. So over here, I know psi of, let's just say psi is equal to 0, and here psi is equal to 0. That means that at the boundary point, psi has to be 0 also. That means psi of 0 is equal to 0, and psi of A is equal to 0, right? Because I have my well going from 0 to A. So let's apply this boundary condition first. So psi of 0 equals 0. And I'm going to put in 0 for x. So that's up here. I have A sine of 0 plus B cosine of 0, because I put in x for 0. Well, cosine of 0 is 1. Sine of 0 is 0. So this term's gone away. I get B. B times 1. So that means B equals 0. So that whole term's gone. Now, for the other boundary condition, psi of A equals 0. I already know B is equal to 0. I have 0 equals A sine of Ka equal to 0. This is 0 if Ka is n times pi, where n is 1, 2, 3, 4, I guess 0. No, let's just say 1. So this sets a condition on k. I can't have any k that I want. I can only have certain k's. And this shows that the system is indeed quantized. It's kind of a big deal. Okay. So I can go back up here. Now if k is n pi over a, and I put that in up here, then n pi over a is equal to that. So that's kind of important. N pi over a is equal to that, square root 2me over h bar. But this also, well, I mean, look, n changes, pi is constant, a is constant, h bar is constant, the mass is constant. That means that I can only have certain values of e. So let's solve this for e. I'm going to square both sides. N squared pi squared over a squared equals 2me over h bar squared, or en is going to be equal to n squared pi squared h bar squared over 2ma squared. So those are my energy values, right? I can put in n equals 1, 2, 3, 4, 5, and I get my energy values. Okay, so we have a function, but we still don't know everything, right? Because I have this. Psi as a function of x is a sine kx. But I found k, but a could be anything still. Because when I take the derivative, it's just still there. Let's put this all together and find my total function, which will not be complete. Psi of x and t is f psi, so it's e to the minus I e over h bar t times a sine kx. One of the things that we find out also is that the probability density is going to be equal to p, or they use rho, I can't remember. It's the complex conjugate psi star psi. And that means that if we want to find the particle somewhere, if the particle has to be somewhere, the total probability of finding the particle has to be 1. So 1 is going to be equal to the integral from negative infinity to infinity psi star psi dx. And this is called normalization. Let's just say normalize. If I do that here, I get 1, negative infinity to infinity. Psi star is going to be this function, but I replace the i's with negative i's, so I get e to the I e over h bar t. I'm going to put in the other one too. I'm going to keep those two together. E to the minus I e t over h bar. And then I have two of these, and they don't change. A squared sine squared kx dx. And right here you see what's really nice is that e to the I e t over h bar, e to the minus I e t over h bar, that's just 1. So this is going to be equal to the integral of a squared sine squared kx dx. And we already said that the particle can't exist lower than with negative x or greater than x equals a. So we only have to integrate from 0, x equals 0 to a. And when we're going to set that equal to 1 and then use that to solve for a. It's not the simplest integral unless you use a trick, but we're going to use a trick. Okay, so let's put our integral right here. And you may just say, I'm just going to look that up in an integral table. You could indeed do that, but that's not that much fun. A squared sine squared kx dx equals 1. Okay. So the first thing I'm going to do is to use I'm going to use two trig identities, and I know you could just use one because you could but I don't know. This is how I do it. I know the following: cosine of, I'm going to write this as cosine of 2k. No, I'll write it the identity. Cosine of 2x is equal to cosine squared of x minus sine squared of x. This comes from cosine of alpha plus beta equals, and you get a cosine, but if I put in x and x, I get 2x, and then my term gets this. That's where it comes from. I also know that sine squared of x plus cosine squared of x is equal to 1. So cosine squared of x is equal to 1 minus sine squared of x. Let's put this in up here. So I get cosine of 2x equals 1 minus sine squared of x. I'll just put that in right there. Minus sine squared of x. And that is equal to 1 minus 2 sine squared of x. Now I can solve this for sine squared of x, and I get sine squared of x is, I'm going to have to add that to the other side and then divide by 2. So I get 1/2 times 1 minus cosine of 2x. That's the identity I'm going to use up here. Now, I don't have x, I have kx, right? So I'm going to have to put kx instead. But I can write this as the integral from 0 to a squared comes out front, the 1/2 comes out front, I don't really need that, 1 minus cosine of 2kx dx. Parentheses, right there. Okay. Now that I can integrate. So let's do it. I have, and this is equal to 1. So 1 is equal to a squared over 2. The integral of 1 dx is just x. The integral of cosine, if I take the derivative of sine, I get, I'm blanking out here. If the integral of cosine is negative sine, right? Then this is going to be negative sine because this is going to be the integral of sine. But then I had this thing in here, so I have to divide by 2k. So I get minus 1 over 2k sine 2kx from 0 to a. And let's just double check. So if I took the derivative of this, I'd get cosine, and then I'd multiply by the 2. Yeah, okay, that works. Now I can evaluate my limits. I get 1 is a squared over 2 a minus 1 over 2k sine of 2ka, and then I subtract 0, and then if I put in 0 right there, I get 0 too, so which is plus 0. Now, remember that k is equal to n pi. That's what we said, over a. And so if I put that in up here, I get 2 in pi. And so the sign of 2 in pi is going to be 0, right? Because no matter how many times I'm going to go around 2 pi times every time, it's the same as sine of 0. So that's 0. And I get 1 equals a squared a over 2, or a is the square root of 2 over a. Is that right? Yeah. Yay, I got it. So if I put the whole thing together now, I have psi of xt is going to be equal to f. Well, let's put the a up front. Square root of 2 over a, e to the minus I. I forgot it already. Is it? The e. Oh, here it is. Put it over here. E. That's right. E. E t over h bar, and sine of k x, where k is equal to n pi over a, and e is n squared pi squared h bar squared over 2ma squared. There you go. Classic physics problem in under 30 minutes too. The end.